Hello, and welcome to the ARSET training, Assessing the Impacts of Fires on Watershed Health. My name is Sean McCartney, and I'm an ARSET trainer based at NASA's Goddard Space Flight Center in Greenbelt, Maryland. It's a pleasure to welcome you all to the second part of this three-part webinar series. The following slides provide an overview of the training. After participating in this three-part training, participants will be able to analyze the key fire science criteria to select the appropriate data from satellites and instruments for a given watershed. You'll be able to distinguish, compare, and contrast the biophysical conditions pre- and post-fire. You'll be able to acquire land use and land cover maps for the region of interest, select river basin and sub-basin boundaries for your region of interest, and recognize how to apply the Soil and Water Assessment Tool, a river basin scale model, to simulate the quality and quantity of surface water and groundwater. The prerequisites for the webinar series are listed below, with links to each of the training web pages. We encourage you to go through these materials to better prepare you for the content covered throughout the three-part training. So why is ARSET hosting a webinar on the impacts of fires? Well, wildfires can disrupt transportation, communications, power and gas services, and water supplies. Wildfires tend to lead to a deterioration of air quality and loss of property, crops, resources, animals, and people. According to the National Institute for Occupational Safety and Health, children, the elderly, and individuals with underlying health conditions are particularly vulnerable to the health effects of decreased air quality caused by wildfires. Part 2 of the webinar series will be focusing on Earth observations and the Soil and Water Assessment Tool for assessing post-fire water quality in watersheds. As a reminder, the homework will be available on the training webpage starting July 13th, with the due date of July 27th. A certificate of completion will be awarded to those who attend all live sessions and complete the homework assignment before the given due date. The objectives for the second part of the webinar series are as follows. By the end of part 2, participants will be able to identify physically based model components necessary to run a SWAT model to predict the impact of management on water and sediment in a watershed, ingest Earth remote sensing data into SWAT model using NASA Access, and recognize best practices used to conduct calibration in SWAT. Questions are encouraged. If you have any questions, please put them in the question box and we will address them at the end of the webinar. Feel free to enter your questions as we go. We will try to get to all the questions during the question and answer session after the presentations and demonstrations have concluded. The remainder of the questions will be answered in the question and answer document, which we will post to the training website about 1 week after the training has completed. Listed below are the trainers for today's webinar. Dr. Ibrahim Mohammed is a senior research scientist in the Hydrological Sciences Laboratory at NASA's Goddard Space Flight Center. His research interests span physical and statistical hydrological modeling and the relationship with climate and land cover, as well as integrating and synthesizing water-related science and engineering research activities to meet the growing demands for integrated professional data analysis. Dr. Amanda Lopez is a geoscience researcher in the Water and Ecosystem Group at NASA's Jet Propulsion Laboratory. Her research focuses on using NASA remote sensing methods and data products to study water quality, coastal ecology, and marine resource management. We'll now transition to Dr. Mohammed to identify physically based model components necessary to run a SWAT model to predict the impact of management on water and sediment in a watershed. Ibrahim, over to you.
Hello everyone, my name is Ibrahim Mohammed. I'm a senior research scientist at the Hydrological Sciences Lab, part of NASA Goddard Space Flight Center, located in Greenbelt, Maryland. Today, I will be presenting an overview of a physically based hydrological model, namely the Soil and Water Assessment Tool, and a hydroclimatic tool, that is NASA Access. Following my presentation, my colleague Mandy Lopez will highlight a case study work on using the Soil and Water Assessment Tool to assess post-fire water quality in watersheds. The second session, titled Earth Observation and the Soil and Water Assessment Tool, SWAT, for assessing post-fire water quality in watersheds, is part of advanced level training webinars on assessing the impacts of fires on watershed health. So this is now the first part, which is the SWOT model overview and NASA access. So let's begin with that. So for today's presentation, we will discuss how to set up a soil and water assessment tool model project. We will be giving details on the SWOT model input data needs, various output, calibration, and verification. We will also introduce a new tool that can provide ready formatted, processed, easily ingested remote sensing data needed to run the soil and water assessment model. Then my colleague will be doing the later part, which is analyzing post-fire water quality data simulated by a soil and water assessment tool model configured over a case study in California. So as you can see here, these are two examples from the soil and water assessment tool configuration. You can see how the detail from different layers that is going to help us to answer a question that is being posed for any watershed study. Let's now go to the SWOT overview. The SWOT is a widely used model in assessing soil erosion prevention and control, non-point source pollution control, and regional management in watersheds. For instance, it has been used to address water management, land use change, and agricultural chemical yield related challenges. The SWOT model development is attributed to several federal agencies and academic institutions, namely the United States Department of Agriculture, USDA, Agricultural Research Service, ARS, the Agricultural Research Service and Texas A&M University, and United States Environmental Protection Agency, EPA, as well as other agencies. I encourage the listeners to visit the SWOT main page to learn more on the SWOT model development efforts. So if we can try to summarize SWOT into few lines, here on your right, you see a hydrograph, and you would notice that this hydrograph is calculated at the Mekong River Streamflow Station in Laos. Often we use or we want to understand the variability of streamflow due to climate or management or human imprint or land cover change. So SWOT is a good modeling candidate that can support applications to solve such challenges. The Soil and Water Assessment Tool, or SWOT, modeling structure combines several components such as hydrology, weather, sedimentation, soil temperature, crop growth, agricultural management. The Soil and Water Assessment Tool modeling units are cells, subwatersheds, hydrologic response unit, and usually they call it HRU, and point sources. It is essential to understand how the soil and water assessment tool model deals with simulating various processes. That means care should be given in representation of interactions and processes within a watershed. And this is usually the case when we are formulating the HRU. A nice effort by Iowa State University in collecting, analyzing, and maintaining SWOT water and assessment tool literature database can be visited. And you can see here at the top of this slide, I give the link so that you can visit that database. So, and this database is a good source for scholars when working with the SWOT model and its utility. It has been nicely organized, and you can easily find recent articles related to development, related to applications, and within the application itself, it has ways to identify um, uh, different applications easily. Let's now look at the processes that are covered by SWAT. The SWAT model, as you can see in this figure, covers several processes. We can name here upland processes, channel or floodplain processes, transmission losses, evaporation, and sediment routing. Looking at the upland processes that are covered by SWAT, we can see that they cover hydrology, sedimentation, and other processes as well. Channel processes cover Muskingum routing method, which uses a conservation of mass approach to route an inflow hydrograph. Evapotranspiration processes, they cover different methods such as Penman-Monteith, Bristol-Taylor, and Hargreaves methods. Knowing the key processes simulated by the SWAT model helps in addressing the problem that we want to study and guide our decision in analyzing the soil and water assessment tool model simulated results. After that, we will look at the SWAT input data. As we can see, the SWAT needs input data, and input for the SWAT model is defined at one of several different levels of detail, such as watershed, subbasin, or HRU. Unique features such as reservoirs or point sources must have input data provided for each individual feature included in the watershed simulation. For spatial data, the SWAT model needs a digital elevation model, DEM, for the study area, a soil information, and a land use land cover layer. For MET data input, SWAT model needs precipitation data, minimum and maximum air temperature data, solar radiation, wind speed data, etc. In situ observations are also needed, such as reservoir rules and treatment plant operations. Stream flow and sediment data are needed for calibration and verification. Looking at the time series on your right, we see an example of time series data input for the lower Mekong River Basin. Annual precipitation in millimeters here are colored in blue. And we have also the mean annual maximum air temperature in degrees Celsius, as well as mean annual minimum air temperature in degrees Celsius. This input data is needed when we are setting up the SWAT model. Now, if we continue on looking at the SWAT output, we have several output files that are generated in every SWAT simulation. The SWAT model user can control the printing of output files by editing what we call the master watershed file. So this master watershed file is very, very important file because it controls what output the model will spit. Average daily values are always printed in the HRU, subbasin, and reach files, but the period they are summarized over will vary. That means it can be daily or monthly or annually. The output files may include all daily values, daily amounts average over the month, the year, or the entire simulation period, depending upon the user need that has been translated or configured in that master watershed file. If we look at the hydrologic cycle, this is a schematic that shows you an overview of the processes that SWAT capture. And components of water balance, as we can see, they are influenced by climate and physical characteristics of the watershed, such as the river reach network, land use, and soil. The SWAT model partitions the precipitation that you can see that's coming to the land into various hydrological processes, such as surface runoff, evapotranspiration, infiltration, percolation, lateral flow, return flow, and recharge to deep aquifer, etc. Here we can see different compartments such as the root zone, the shallow or unconfined aquifer, and deep aquifer. So these compartments basically they are um, taking the water flux from compartment to another, and in each one the processes involved, SWAT is able to capture that by setting up different equations. Another cycle that's very important and it is captured by SWAT is the phosphorus cycle. And the three major forms of phosphorus in mineral soils are organic phosphorus associated with HUMS, insoluble forms of mineral phosphorus, and plant available phosphorus in soil solution. Phosphorus may be added to the soil by fertilizer, manure, or residue application, as you can see in the schematic. Phosphorus is removed from the soil by plant uptake and erosion. Unlike nitrogen, which is highly mobile, phosphorus solubility is limited in most environments. Now, after defining the model inputs and model outputs, and just giving an overview of the hydrologic cycle, the phosphorus cycle, and how the processes are configured into SWAT, we will cover some details about the model calibration. Model calibration is a very, very important aspect when we are conducting a modeling experiment. SWAT uses many parameters to describe typical soil, plant growth, land cover, reservoir, and agricultural management characteristics. Luckily, there is the SWAT calibration and uncertainty procedure software package, which is called SWAT Cup, which can assist in obtaining calibrated values for model parameters. SWAT Cup program could be used to perform calibration, validation, sensitivity analysis, one at a time, and global, and uncertainty analysis. So here I'm giving an example of a calibrated model over the lower Mekong River Basin. As you can see on your right, there are 6 stations. These stations across the lower Mekong River, and we can see the metrics that can give us an understanding of the calibration of the model. And these metrics are here defined by the NSE and the era of simulated flow. On your left, this is just a figure that shows you the locations of these stations that we used to conduct the calibration. After we calibrate the model, we wanted to verify the model. And this step is done after calibration. So usually verification step is very, very important because we normally examine the model behavior during times beyond the calibration periods. As you can see in the previous slide, we basically calibrated the model for a specific time period. Now we will assess the behavior of the model within time periods beyond that calibration time period. This is basically important because the SWOT model verification assures the model is capable of simulating processes outside the training periods. And here, the same 6 locations that we did in the calibration, we examine them for the verification step. And we assess the verification results by obtaining the national Sutcliffe efficiency metric. After covering the first part, which was the soil and water assessment tool, now we will go to the second part, which is the NASA Access. So what is NASA Access? NASA Access is an open source platform for accessing and presenting quantitative remote sensing Earth observations and climate data products in an interactive format so that scientists, stakeholders, and concerned citizens can engage in the exploration, modeling, and understanding of the data. On your right, you will see the GitHub landing page for NASA Access. And NASA Access is a free tool and it is an open source, as we just said. So you can easily test, utilize, and examine to see how it can help you in your modeling exercise. NASA Access is available into different formats, as we can explain in the next slides. So looking upon this animation, which shows rain data collected by the Global Precipitation Mission, GPM Core Observatory, one might ask, how can we ingest this data into SWAT or any other hydrological model? NASA Access platform is developed to assist you in answering this question. Basically, NASA Access platform provides formatted data that can be ingested into any hydrological model. Moreover, NASA Access has a web-based application that can be used to visualize remote sensing data. So NASA Access is a modular, which means it can be hosted on public and private servers. Here we give the existing functions of the NASA Access platform. NASA Access platform is an ongoing platform. So every time we add new function and new tool to the platform. And here we can group them into two main groups, climate and weather. In the climate group, we have functions that can access and reformat data from CMAP5 and CMAP6 downscaled data sets. And in the weather group, NASA Access can access and reformat data from GPM, GLDAS, and various functions that include averaging over the centroid of the study area domain or collecting the available grids within the watershed domain are available. The benefits. What are the benefits of NASA Access? NASA Access can be summarized into two main points. It can give us time because it will save time for scientists tasked with analyzing weather and climate data as well as developing hydrological model. As we just showed in the previous slides, if you have that GPM data and you wanted to use it for your SWAT model, NASA Access can help you in doing that. NASA Access can help you to process downscale climate data from CMAP5, CMAP6 collections. NASA Access can help you to access GLDAS data products and so on. And the other benefit for NASA Access, it's bridging the gap for non-technically trained stakeholders and decision makers charged with water, climate, and environmental management decisions. This basically is very, very important, especially with the web-based feature of NASA Access, because you can visualize, you can analyze the remote sensing data without the need for any advanced software program. Here we give images of the current NASA Access R library and as well as the Conda package. So NASA Access is available as an R package. You can go to GitHub, install it. NASA Access is available as a Conda package. You can go to Conda Forge and easily install it in your environment, Conda environment. Here we give the NASA Access web-based application home window, and this is an app that you can install in your private laptop, machine, server, and it can do all the jobs that NASA Access have, as well as giving another feature, which is visualizing the data that you processed. So the user can upload a shapefile and a digital elevation model for his domain, for his study area, and then select any available function with the temporal period uh, desired. After processing the data, the user will receive an email saying the data is ready, so he can then start visualizing and analyzing the data products. Here, I give a small example that explains, for example, when we are accessing precipitation data from the near real-time product, GPM NRT product. Here the latency is 1 day. You can see that on your left. This is the function that you need to provide some input to it. Basically, what directory that you wanted the data to be at, and give the shapefile for your study area, the digital elevation model for your study area, and then what are the temporal period that you are interested at. After you provide this and you run the function, it will basically go and translate this into URL, and that URL is going to go and communicate with NASA servers and obtain the needed data products and format it in a way that can be seen on your right as time series or a figure that can be used in your analysis. Here, the same example, if we just look at it from RStudio, as you can see on your left, top left, this is the script, basically the same function that I just explained before. And on the bottom, you see the R console, how after installing NASA Access and running this function, this is the results that you will get. On your right, you will see um, files that we call it SWAT ready weather input data. So if you wanted, for example, that data to be an input for a SWAT model, you can just take these files and put it in your SWAT model projects. These files are ready formatted, so you don't need to do anything with it. A SWAT will be able to read it and fill the database with the data smoothly. This is the flow chart that summarizes the web-based NASA Access application. It begins from the left by the available data products that NASA Access now have linkage to, and then it will have the user inputs as shapefile, digital elevation model, the time period that is the user is interested at, and after that, this will be translated into um, code that is going to create URLs, and that URLs will basically communicate these downloads from NASA servers, and then obtain the data, process it, format it, and after that, make it easy for you to visualize to ingest into your hydrological modeling experiment. So in summary for this part, the Soil and Water Assessment Tool, SWAT, is a small watershed to river basin scale model used to simulate the quality and quantity of surface and groundwater and predict the environmental impact of land use, land management practices, and climate change. NASA Access is an open source platform for accessing and presenting quantitative remote sensing Earth observations and climate data products. NASA Access can be used to ingest Earth remote sensing data into a SWOT model. With that, I conclude the first part of this second session, and I pass the microphone to my colleague Mandy to continue with the second part of this session. Thank you for listening. Mandy, the floor is yours. Thank you.
All right, thank you, Ibrahim, for introducing the initial SWAT content. I'm Mandy Lopez. I'll be talking more in depth about how we evaluate fire impacts on watershed health using the SWAT model. So to give some background first about why we're interested in modeling fire at all, we have seen that globally wildfire activity is increasing in frequency and severity. This is happening as climate change progresses, and we see changes in precipitation patterns and so on. So as these fires become more prevalent, we want to understand what this means for watersheds. If you look at the upper right-hand figure, you can see this kind of graphic demonstrating a fire burning through a land surface. You lose vegetation cover, you increase erosion, and this results in increased amounts of sediment and burned material entering into rivers and streams, which end up in lakes, reservoirs, and the ocean. Our project wants to understand what this increase in sediment loading, which can also have increases in nutrients or contaminants alongside it, what does this mean for the ecology of lakes, rivers, and the coastal ocean? For example, as increased sediments enter the coastal ocean, we might see decreased water clarity, which could impact primary producers like phytoplankton or kelp that rely on sunlight penetrating the water column. Another impact that we're thinking about is as sediment loads or nutrient loads like nitrogen or phosphorus increase into water bodies, what does that mean for algal blooms? Will we see increased eutrophication or things like that? So our big picture goal here is to try and understand how hydrologic processes are being impacted by wildfires so that we can in turn get a better understanding of how our aquatic ecosystems are impacted. So the soil and water assessment tool, which you've already heard quite a bit about, is a watershed model. It goes by the name SWAT commonly. In this demonstration, in this study, we're going to be looking at simulating stream discharge and sediment load. And the model is typically calibrated using in situ observations of discharge or sediment load at monitoring gauges. In the scope of this training, we will not get into the model calibration and validation steps, but I'll briefly comment on them here. So this diagram that you're seeing at the bottom of the slide is just a schematic walkthrough of what the SWAT modeling process is like. Your step one would be to prepare and input some basic information into the SWAT model. That information includes elevation, land and soil cover, and climate data, particularly precipitation and air temperature data. Once you feed these inputs into SWAT, it will run and simulate stream discharge and sediment load, which is step two shown in this workflow. In step three, you move on to model calibration, where you do a comparison of the model simulated discharge and sediment load to the in situ observations of discharge and sediment load. And when you compare simulated and observed, in the calibration step, you are tuning model parameters. You're tweaking and turning different parameter ranges to try and get the best possible fit between simulations and observations. When you have a nice fit, you move on to model validation. And in this step, you're taking a new, fresh subset of observational data and doing a second comparison of model simulations to in situ observations. The difference is that during validation, we are no longer tuning any of the model parameters. Nothing is changed. It is all held constant from step three in calibration. So in validation, when you do your second comparison, you're looking to see, do you still have a good fit between simulations and observations? And if you do have a good fit, then we consider that the model is both calibrated and validated. It's demonstrated to replicate on the ground processes well enough based on our observational data that we can move forward and interpret the actual model outputs, which is step 5. In this training, I'll be doing a demonstration of step 1, where you're actually setting up the SWAT model with the different input data sets. All the other steps are going to be beyond the scope of what we covered today. The SWAT example that I will be demonstrating is of the Woolsey fire, which burned near Malibu, California in 2018. If you look at the figure on the right, this is Southern California, near Los Angeles, near Malibu. The blue outline is the watershed, the Malibu Creek watershed that we'll be looking at today. The pink shading area is the burn extent of the Woolsey fire. The black triangles are climate data stations. This is stations where we have precipitation and air temperature data that will be fed into the model from. The red star is the location of our in situ monitoring gauge. This is where we have actual observations of discharge and sediment load that we'll be using, or that you would use to calibrate and validate the model, which again is not going to be covered in this training. In the table on the left, you have kind of just a recap of what I've talked about. The SWAT inputs, what they are, elevation, land cover, soil cover, and so on, and then the data source. So when I demonstrate, you're going to see different data sets, and this provides you details of where those data came from. One thing I want to point out here, and I'm about to get into more detail, is about the land cover. Because in our project, we're looking to simulate fire within a watershed, which means we have to find some way to tell SWAT that a fire happened. And in our study, we've chosen to do that using this land cover input. What we're doing is taking a pre-fire land cover layer, in this case is the National Land Cover Database from 2016, and we modify it with a burn severity map. For this study, we're using a soil burn severity map from the California Geological Survey. So what we end up doing is creating 2 different land cover inputs, one that represents pre-fire conditions in the watershed and one that represents post-fire conditions. This slide is showing just a little more detail about that post-fire land use map that I'm talking about. So we start with your unburned or pre-fire land use cover. You overlay soil burn severity, which the left figure, this is a map of soil burn severity for the Woolsey fire that we used. We overlaid land cover with soil burn severity, and wherever those 2 layers intersected, we did a reclassification. So that if, for example, before the fire, the land use was a forest area, but during the Woolsey fire, it had a low burn, it would then become reclassified to forest low burn within our model. And this new land cover class, forest low burn, would have unique parameter changes, which I'll talk about in a little bit, that represent fire conditions in that particular location. So this, what you're seeing on the right-hand side, this is the reclassified post-fire land use map, where we already did the overlay of pre-fire and burn severity to create this new land cover output. All right, so on this slide, it details the different changes that are made to parameters within burned land cover classes in your new post-fire land use map. You change curve number, modified universal soil loss equation K factor, and leaf area index parameters. The reason these parameters are changed is because they each relate to something that we associate with fire occurrence. For example, curve number and K factor are related to soil, be it soil erosion or permeability, and leaf area index factors are related to plant cover, evapotranspiration, and so on. In our model, we decided to increase the curve number and K factor, which would increase surface erosion and runoff, which is what we expect after a fire. And we also decided to reduce leaf area index parameters to reflect vegetation loss on the ground. When I go through the demonstration, I'll give more detail and show more explicitly what I mean by changing these parameters. Next thing you'll use is the land use update tool. This is a feature in SWAT that allows the model simulation to run using one designated land cover input and then switch to a separate designated land cover input during the model run. So in our case, the Woolsey fire occurs in November of 2018. Using the land use update tool, we run the SWAT model using the pre-fire land use input up until November 2018. And then when the model reaches that date, it will switch to using the post-fire land cover input that we created. Now, in order for the land use update tool to be activated within SWAT, there are a number of input files that have to be created. And there are a few different ways out there to make these files and set up your model to activate the land use update tool. In my demonstration, I will be showing the first method that's listed, the SWAT_LUC tool. But there are also a couple of others which I have linked as well in case you want to try those out. And for reference, the two figures that are shown here on the left, it is the pre-fire land use. On the right, it is the post-fire land use. So you can visibly get a sense of how land use changed pre and post-fire. Now, although we are not going to be going through calibration and validation, I wanted to show just a little bit about how this particular example is calibrated and validated, and perhaps it can help others if you decide to pursue this and get into this step. But in our case, we have one monitoring gauge, and it has daily discharge for the 20-year study period, which is 2000 to 2020. For our model, we are interested in using data pre-fire for the calibration and validation. We don't want to use any of that data for calibration and validation because we want to interpret that. That's when the fire happened and we're interested in investigating. So in our approach, we wanted to look at a subset, a chunk of data that's happening between the years 2003 and 2016 or so. And of that time span, we wanted to break it up into a calibration subset and a validation subset. And the way that you do that is to look at your hydrograph or look at your precipitation. In this case, the graph is showing discharge on the is the dark gray line, and the vertical y-axis on your left has the values for that. Precipitation is a dashed blue line, and the vertical y-axis on your right is the graph or the values for that. And time is shown up across your x-axis. When we subset data into calibration and validation chunks, we want to choose periods of similar wet-dry seasonality. Or in other words, you don't want to have all of your calibration be set in a dry period and all of your validation be set in a wet period, because then you're choosing two hydrologically quite different data sets. You want to have comparable subsets of data. So what you're seeing here is the green shading is showing the time period that we used for calibration. The yellow shading is showing the time period that we chose for validation. And if you look at the metrics shown at the bottom of the slide, there's a similar stream average discharge in these time periods with a similar standard deviation. And this is what we want to see, that there is both wet and dry periods covered within both subsets. And on this slide, we just have some very preliminary results of our modeling efforts. This is showing you the post-fire period, which is covering the years 2018 to 2020. The dashed kind of green line is showing you where the Woolsey fire occurred. This is the subset of model data that we're actually interpreting for our study. We want to understand how the Woolsey fire impacted sediment load and discharge. And as you can see, following the Woolsey fire, there's big peaks in both in the simulated and observed variables, the red lines and the blue lines. It turns out that following the Woolsey fire, almost within a month, we had huge rains, a big rain event that came. So we had fire and then almost immediately a lot of precipitation that allowed us to capture this big peak that you're seeing on these graphs. In our modeling effort, you can see that there's a pretty decent matchup between the blue and red lines, between our simulated and observed, which is demonstrating that our model is currently doing a pretty good job of capturing that first post-fire peak immediately following the Woolsey fire. If you look further down that timeline toward the end of 2019, early 2020, there are some smaller peaks where the matchup between simulated and observed isn't as great. And we're hypothesizing, and something that we're actively investigating, is that perhaps this is a recovery signal, that our model, that the results that you see here are tuned for post-fire conditions, but perhaps pre-fire conditions are more representative of those later peaks in that, or in other words, that our watershed is recovering. And so that's something that is an ongoing investigation. To kind of shift away from that Woolsey fire example and just zoom out, our study is not the only one to try and apply SWAT to fire impacts in a watershed. On this slide, I've listed a couple of other examples in the literature. Some previous work has shown that SWAT can estimate post-fire discharge sediment load and other water quality parameters, similar to what we have found. In 2017, Basso et al. Showed that fire-impacted watershed had increased nitrate and phosphate, which in their case, they looked at local regulatory thresholds and saw that those increases had regulatory implications as well. So this is an example where the SWAT model, along with fires in a watershed, was used to talk about nutrient loading and pollution. Havel et al. Particularly looked at runoff and sediment post-fire in a Colorado watershed, and also were able to constrain and tune the model to capture what they observed with monitoring gauges. So the table down here is showing kind of a summary from the Basso et al. Paper, where in unburned versus burned, or in their case, they put wildfire scenarios, they could capture the impacts of wildfire within that watershed that they modeled. So if you're interested in getting into more details about how to tweak and change your SWAT model to capture fire, I would direct you to these papers. There's not a whole lot out there yet. It's still kind of an emerging field, but these papers are good for getting a better sense of how it's done. And in summary, our project is really interested in understanding how fires can increase stream flow, sediment load, and nutrient load in watersheds. Other previous work have demonstrated that this does occur, and we are interested in using SWAT to quantitatively constrain the changes in discharge, sediment load, and nutrient load. This application of the SWAT model, as I just mentioned, is pretty new and emerging, so there is lots of different ways that you can change SWAT to try and capture fire, and our way is just one of the many ways that it could be done. So if users are interested in exploring this more, I'd be happy to chat more about that. All right, so in today's demonstration, I'll be using ArcSWAT, which plugs into ArcGIS, but there is also a QSWAT version of this, so that you do not need to use proprietary software. Just wanted to direct your attention to this for users that don't use ArcGIS. This recording is going to be available on the training website, so you'll be able to go back and follow at your own pace. Today I'll be moving through it quite quickly for time's sake, but there will be a longer video demonstration available as well as a step-by-step guide. So afterward, you can go take a look at those materials if you'd like to get a better sense of how to do this. Okay. So the first thing I'll do is start by opening a blank untitled ArcMap document. And up here is the SWAT tool, ArcSWAT interface plugin. I'm going to open a new SWAT project. I do not need to save my blank document. We're going to set up our project. For the project, you need to have a DEM, a land use. A mask is optional. In our demonstration, I'll be using a mask. To set up your project, you point it to the folder that has your materials. Now, if you go back to that folder, you'll see that it is populated with SWAT databases and some other files. Next, you're going to delineate your watershed using the watershed delineator tool. First thing will be to read in your DEM. So we'll go back to that folder, select your DEM, load it in. You can see it loads, it populates in the background. I'll read in a mask, which in our case tells ArcSWAT to only use an area of our choosing. You can see this black raster is the mask. I know that it covers my watershed of interest, and it just helps cut down on some of the processing that ArcSWAT will have to do. Next, you'll click Flow Direction and Accumulation. Under this area, I'm going to modify it to be 250. There's more information about this in the long form video guide as well as the step-by-step guide, so I won't describe why I'm doing that now. Next thing you'll do is click Create Streams and Outlets. You see in the background, different stream networks start to be defined. Next, you'll move to the outlet and inlet definition box. This is where you're going to point to your monitoring gauge locations, which is a .dbf file. Again, more details are in the long form video as well as step-by-step guide. This is how SWAT knows where your monitoring gauges are in your watershed. Next, you're going to tell SWAT where your watershed outlet is. And then click Delineate Watershed. So now you'll see that SWAT has created a boundary for your watershed, including the stream network, which is in blue, and subbasins, which are outlined in purple. You're going to next click Calculate Subbasin Parameters. When the process completes, you can click Exit on the Watershed Delineator menu and save your project. Now you'll see your watershed as well as some different features about it, like the stream reaches and basin, things like that. Different outlets are all populated for you to toggle on and off. After your watershed delineation, you're going to modify some databases in your project. This only happens in your post-fire project. If you're doing a pre-fire model, you don't have to worry about these extra steps that I'm about to show. But what you need to do is modify some land uses before we move on to the next step. So you go to your project folder, to the SWAT 2012 database, open it up. Open the crop tab. And we're going to add in some information. These are adding in the burned area land uses. Since this is a post-fire model, we copy and we paste. We're going to add some more land uses to the urban tab. These are urban land use classes. We'll repeat that for the urban default as well. Let's fix those. Now that we've made these changes, we'll save and close. Now that we have done that, we can go back to our SWAT project and define our HRUs. So now you're going to read in your land use layer. Okay. I'm going to select value. This is how SWAT understands what the different land use codes are. I'm going to use a lookup table so that SWAT can read more detail. Okay, so now we've loaded our land uses, including the different burned areas that we changed using burn severity, and SWAT has been able to understand it using the coding that we described. For soils, we're going to use the StatsGo database that comes with SWAT. I will not change anything and hit reclassify. For slope in our watershed, we're going to be using 3 different slope classes. There's detail about how you choose slope classes and define them in the longer version, as well as the step-by-step guide. For this case, we're using 3 classes with different slope grades defined between 0 and 9%, 9 and 18%, and greater than 18%. I'm going to click Create HRU Feature Class for my watershed because it is a small watershed. If your watershed is large, do not use this feature. And then click Overlay. Okay. Now you have defined HRUs, or I'm sorry, now you have created HRUs and we're going to fine tune them. I'm going to use some thresholding to eliminate very small percentage cases where land use is less than 10%, or soil class is less than 10%, or slope class is less than 10% of an HRU. We're going to disregard those because they are a very small percentage of the area. Because this is the post-fire model and we have burned areas that we want to make sure we don't ignore, we're going to institute an exemption so that none of the burned areas are going to accidentally get kicked out based on the thresholds that I just set on that previous tab. So I selected all of the burned land use classes and exempted them. They will be kept in the model. You'll notice I left low burn and moderate burn water, WA, in the out of the exemption on purpose, because burned water doesn't really represent anything. So that's not something we need to keep in our watershed. Now we'll disregard elevation bands because in our particular case study here of Malibu Creek watershed, we do not have to worry about elevation that interferes with snow and ice and things like that. Click Create HRUs. Okay. Now that that's completed, your HRUs have been created, and you can click on this HRU on Analysis Reports if you'd like to see some information about the different HRUs and how they were differentiated in your watershed. So this is just a resource you can look back on. You'll see along the side here, we have all of the inputs that we've loaded to date so that you can toggle on and off if you want to take a deeper look at how your soils or your slope classes or land uses are distributed in your watershed. Next, we're going to use the Write Input Tables feature. Click on Weather Stations. We're going to use a weather simulator. If you're in the United States, you can use any option except WGEN_user. This is only used if you're in a watershed outside the United States. I'm going to select this first one. For rainfall, we have precipitation data prepared for use in the model. I'm going to select rain gauges and then navigate to your project folder. And you're going to read in your precipitation header file. For temperature data, you're going to click Climate Stations, go to your project folder, and read in your temperature header file. For relative humidity, solar radiation, and wind speed data, we're going to use the simulation option that SWAT has. And click OK. Processing is complete. You can close out of this window, and we're going to save the project. Next, we're going to write the SWAT input files. This is under Write Input Tables, Write SWAT Input Files. You're going to select all and then click Create Tables. You'll get this pop-up and just click Yes. Right, click OK. Now you can close out of this menu and save your project. All right, this is only again for post-fire. We're going to do some more database edits. If you're in a pre-fire model, you can skip the next little bit that we're going to do. I'm going to save this project and close it. Now you'll navigate to your project folder, and we're going to make some edits in the project Microsoft Access database. Open this up. You're going to edit. First, we'll edit the soil database. So double-click soil. Parameter we want to change is going to be the SLK. Here it is. So first, I'll make sure that this is sorted from smallest to largest. Okay, good. That sorting simply so that I can copy and paste from this example Excel file. When you make these edits on your own, following the demo materials, I recommend doing the sort just to make sure everything is in the right order when you paste. Tend to do a quick visual check just to make sure. I know based on my experience that this is a burned area class, so I'm just going to do a quick double check and make sure, yes, the SLK was one of those changed values. So it looks like, at least at a brief glance, it looks like it copied and pasted correctly. Next, I'm going to change the leaf area index underscore INIT parameter. This is going to be in the management database. Here it is. Make sure this is sorted. Leaf. I'm going to copy. And again, quick visual inspection. Yep, this is a burned area. It was changed. It looks about right. Of course, when you do this, maybe spend a few extra minutes making sure everything copied over correctly. All right, so we'll save the database and close. So now we've made the changes to our project database. We're going to open it back up. Click on our ArcMap document. So we changed a couple of things in our project database, and we want to make sure that SWAT knows we changed that. So we're going to go to under Edit SWAT Inputs, Rewrite SWAT Input Files. We made changes to the soil and management. So we're going to select those two and click Write Files. Done. So now everything is updated. This SWAT project has our little modified inputs. Now we're going to actually set up and run the SWAT simulation. So under SWAT simulation, run SWAT. Just take a glance, make sure this is the correct time period for your model for this project. That is correct. You can modify your printout settings. I'm going to leave it as monthly, which means SWAT's going to give me monthly time step outputs for discharge and sediment and whatever other parameters. NY skip is the model warm-up period. For my model, I'm using 3 years. Under SWAT.exe version, you can choose the version you'd like to run. I'm going to use the 64-bit release. Now I'm going to click Setup SWAT Run. Okay. Once that's done, the Run SWAT option will become clickable. So you're going to click Run SWAT, and next you'll see a interface pop up. And this is the model actually running. In my case, it's 21 years, so you're going to see it execute up to year 21. Okay, SWAT run is successful. All right. At this point, you can close out of this and save your project. Now you're going to go to Read SWAT Output under the SWAT simulation option. The most common files that people like to look at are the outputs by reach, by subbasin, and by HRU. So those are the 3 I'm going to click, but you can see there are many options. I'll import these to the database. Remember that project database we had just made some edits to will now have output files or output tabs that you can go to and look at the model output for. Running SWAT check is optional. This is a very broad brushstroke overview of your model. I'll just click on it to show you for this example. It'll open up a new window. You'll click Examine Model Output, and it'll just give you a very, like I say, high scale, broad scale overview. Here's your simulation length. It was 21 years with the warm-up period. It tells you some stuff about your watershed, and you can kind of click through, and it gives you some nice preliminary estimates of here's what precipitation or curve number or runoff is going to look like in your watershed, and it'll give you some messages about maybe your groundwater ratio doesn't look quite right or things like that. It does this for sediment, for nitrogen, for phosphorus, and you can, so on and so forth. All of these things are just to make you aware. When you actually get into your model calibration and validation is where you can really dig into making changes to tune your model to be more accurate. The save, so optional. because you can continue to tweak within the ARC-SWAT interface. For example, you could go back and make more database edits and then run the model again. And you can kind of keep playing around. And if you want to look at different iterations, this is where saving your simulation will be helpful. So as practice for myself, I always save each simulation so I can go back and look at things if I make changes. Okay. So at this point, you have set up and run your SWAT model. That's all you have to do. But in the case of fire, remember, in order to use the land use update tool, you actually have to set up a pre-fire model and a post-fire model. What I just showed you is post-fire, but you would repeat most of these steps and do a pre-fire as well. Now, to use the land use update tool, which is the feature that bridges the pre-fire and post-fire model together, that requires using some R scripts, but for brevity, we're not going to cover that today. It is included in the long form video as well as the step-by-step guide, so you can go refer to those to implement the tool and the scripts. All right, that concludes the demonstration. I'm going to pass this off to Sean, and I'll be around for the question and answer session.
Thank you, Mandy, for the wonderful demonstration of running ARC-SWAT. To summarize what we learned today, fires have been shown to increase stream flow, sediment loads, and nutrient loads in watersheds. SWAT can be used to quantitatively constrain fire-related increases in water quantity and quality parameters. This application of SWAT is relatively new. There is the potential to continue development. And looking ahead to our third and final part, which is part 3, in part 3, we will focus on identifying global socioeconomic data sets and land cover products useful for assessing the impact of fire on population, infrastructure, and land use and land cover types. Acquiring land use and land cover maps for a watershed of interest, and evaluating the severity of post-fire burns within a watershed of interest. As stated earlier, there will be one homework assignment for all 3 parts of the training. Answers must be completed via Google Form, which can be accessed from the training page on the ARSET website. Homework will be made available on July 13th with a due date of July 27th. Parts 1 and 3 will include hands-on exercises to assess pre-fire risk and post-fire impact on a watershed using Google Earth Engine JavaScript. A certificate of completion will be awarded to those who attend all live webinars and complete the homework assignment by the deadline. You will receive a certificate approximately 2 months after the completion of the course. Below is the contact information for Dr. Mohammed and Dr. Lopez, along with links to ARSET website and social media. We hope you will sign up on the ARSET listserv to receive notifications of future trainings, and please do follow us on Twitter and YouTube. Below are links to SWAT resources for your benefit, along with prerequisites for running SWAT and the NASA Access Data Tool. We will now transition to the question and answer portion of today's training. Thank you. Wonderful. And again, we've been getting some really terrific questions. So thank you to everybody that's been submitting them. And we do have roughly 17 minutes left. So if you do have a question and you've not posted it in the question box, we hope that you will do so. Jumping right into it, question number 1, we can use several tools for the same remote sensing analysis like R, Python, SportLiz, SWAT, Earth Engine, etc. However, what about accuracy? How can we know which tool is able to perform more accurately than others? Or what about their limitations? And I will hand this over to Dr. Lopez to answer question number 1.
All right, can you hear me?
Yep, Mandy, we sure can.
Okay, great. Yeah, so for this question, I get a little bit of information about SWAT uncertainty accuracy, and then I see Ibrahim also added some commentary below that, but I'll just talk to to what I wrote, which is that in this training, we're specifically demonstrating how remotely sensed data can be used as inputs into the SWAT hydrological model. So there, of course, are going to be uncertainties associated with those remotely sensed data sets, which are normally going to be summarized when you go to download that data in the supporting documentation or on the download portal. Aside from that, in SWAT itself, the calibration and validation steps are where you're actually comparing what the model simulates to in situ observations. And there are some statistics that we use to evaluate the goodness of fit between simulated and in situ. And then the SWAT CUP software, which is the calibration and validation software, uses a 95% prediction uncertainty band, or 95 PPU, to constrain the range of model simulations. And that's basically how SWAT addresses the accuracy of its modeled outputs, is to give model outputs within the 95 PPU band, which I kind of gives you more detailed languages on the document here. But all of that kind of bigger picture here is that the uncertainty characterization for SWAT is going to look different than the uncertainty characterization that maybe a remotely sensed data product has, you know, and it's hard to compare those or know which tool is going to be the most accurate. That's, I tried to give maybe a more SWAT focused answer to that question. Ibrahim, I see you have some other details. Do you want to go ahead and talk about what you wrote?
Great. Wonderful. Yeah, thank you. And Mandy, I was wondering, it seems like you're somewhat muffled. Can you try to get maybe as close to the microphone as you can? I think that might help with the clarity. Thank you.
Oh, sure.
Is any better?
Can you keep talking?
Testing.
Yes, perfect. Yeah, that is much better. Thank you so much. Awesome. Great. So jumping into question number 2, in a time of climate change, especially approaching a tipping point, how does calibrating and verifying models make sense? If first and second order statistics are not stationary, how can a model accurately predict the future? And Dr. Lopez, back to you.
Sure. Yeah. So this is a challenge, as we know that climate change is progressing and therefore hydrological processes are going to change. But one way that we can account for this is to model over long time periods that have variable climate conditions, so that you have plenty of model time simulation to work with for calibration and validation. So if you're only modeling over the course of 5 to 10 years, that's relatively short for the scale that climate change can happen on. But if you can run the model for a much longer time period, maybe on the order of 20 plus years, you're hopefully capturing quite a bit of variability in precipitation and air temperature and things like that, so that when you move into calibrating and validating the model, you have plenty of time record to use to kind of train SWAT to capture all of the different seasonality and on the ground conditions, so that hopefully you have confidence that your SWAT model can reflect the range of conditions that your watershed might reasonably experience within the time period that you actually want to interpret data for. That said, which is kind of what we've done in our project, we have a 20-year model period, and we've used as much of that as we can for calibrating and validating, leaving only the few years post-fire for interpretation. And the idea being that if we're pretty confident that our model's performing well in both calibration and validation, that we can then go back and synthetically alter climate variables and then look at how outputs change. And it's not necessarily a like true prediction. It's more of a let me tinker with what the model is doing manually and then see how the output changes. And we can use that in a predictive way to say, okay, if we anticipate that climate is going to change by reduced precipitation and higher air temperatures, what then does the model output under those scenarios? And we kind of call those predictions.
Great, wonderful. Yeah, thank you so much for that. Question number 3. Is there any model like SWAT for assessing the impact of climate change on forest fire?
I personally am not familiar with other models that are being used to evaluate the impact of climate change on forest fires. I see that there have been some others listed here by Ibrahim, NASA, LAS, RESIS, DHS, VM. I personally am not familiar with these, so I would encourage whoever asked this to maybe Google them if they're interested. But for SWAT itself, this application of fire simulation is relatively new and rare. There are maybe a few studies that have done it, ours among them. Yeah, I don't have much more information on that end.
Okay, great. Moving on, question number 4. In the SWAT demonstration, and National Land Cover Database NLCD dataset is used with the California Geological Survey burn severity dataset. Are these datasets available for every state, or are there other datasets available? How often are these datasets updated?
Yeah, so in my case, I can only speak to California since that's where I've worked. I know within California, there are a few different places that have burn severity data sets. California Geological Survey is one of them. It does not have a burn severity data set for every single fire. The California Geological Survey only selects some of the fires in the state. But there are some other databases like the Monitoring Trends and Burn Severity Data product. That one, I believe, has the biggest coverage of fires in the US and maybe beyond. So I would start there. There's also a newer database from a paper that was published last year called the Wildfire Burn Severity and Emissions Inventory. That, I believe, covers most California fires over the last decade or so. I haven't checked that database in quite a while, but I believe they are actively updating it. So for burn severity, I would look, at least for California, at those 3 options. If you're in a different state, maybe inquire with your state's geological agency to see what they have. But for the National Land Cover Dataset, the NLCD, that's updated about every 5 years. And the data portal is pretty well maintained with documentation of when it's being updated and how it's changed.
Great, thank you, Mandy. Question number 5. Are there SWAT tools that will run in ArcGIS Pro?
No, unfortunately, to my knowledge, and at this point, SWAT is not compatible with ArcGIS Pro. Maybe that might change. I have no idea. It seems like the people, SWAT has such a large user base that maybe if there's enough demand, someone somewhere might be persuaded to make it work. But to my knowledge, it does not work with ArcGIS Pro, and it requires certain working versions of ArcGIS. I don't remember them off the top of my head, but I put a link to that question, in the answer to that question, to the website that gives all the details of which version of ArcGIS you would need to use ArcSWAT.
Great. Question number 6. Is it required, excuse me, is it required to have Microsoft access to use SWAT, or can you just use Excel?
I don't believe you need to go out of your way to acquire Microsoft access. when you download and install SWAT, it comes with everything that you need so that when you run SWAT on your computer, it will automatically create that database for you and store the data in that structure. I think it would be helpful if you had the Microsoft Access license so that you could work with those files that SWAT generates more easily, but I don't think you need more than that. That one, maybe when you go to install and use SWAT, I would take a closer look at the manual when you do the installation.
Great. Question number 7. Could you please provide us with some resources to help with model calibration and verification for the tutorial presented today?
Yeah, that I believe it looks like Ibrahim might have put a link to a manuscript, and I can also add some links as well, but there are a good handful of papers by Dr. Karim Abaspour, who is largely one of the prominent developers of SWAT Cup, which is the calibration software. If you go to YouTube and just put SWAT Cup in, you'll probably it'll pop right up, but I'll put some links in this document. There's a large suite of YouTube tutorials for the calibration and validation, and there are some papers by Dr. Abaspour. So I'll put these links in the answer to this question.
Terrific. And question number 8, given different soil characteristics and properties that vary area to area, can SWAT be applied to any geographical area?
Yes, it can be applied to any geographical area as long as you have the inputs that SWAT needs. So, for example, I see in my demonstration, I did it for California, and SWAT has a US Statsco soil database already loaded, but you as the user can define your own soil input from however or wherever you get it from, be it from a state or federal agency or even a soil raster layer that you went out and created and made yourself. You can change the soil input to be appropriate to your area. I'm just looking at Ibrahim's answer really quick to make sure that I did not leave anything out. Yeah, I think I covered what he kind of mentioned here.
Okay, wonderful. And question number 9, is there a version of QSWAT that is compatible with a Mac operating system?
Yes, short answer, yes. I will search around, but this can also just be Googled. There is a version of it. I don't remember exactly what it's called.
Wonderful. Well, thank you, Dr. Lopez, so much, and also Ibrahim, Dr. Mohammed, for doing such a great job in addressing all the questions that were posed by the participants for the part 2. As we wrap up, I want to thank each and every person that did join us today for the second part. Want to remind everybody that this Thursday in 2 days at the same time, we'll be concluding this webinar series when we have the final part. And so we do hope that you'll join us all in 2 days at the same time. I also want to thank our guest presenters today, Dr. Amanda Lopez and Dr. Ibrahim Mohammed. Thank you both so much for contributing this wonderful content and demonstrations using ARC-SWAT in Malibu Fire in Southern California. And I also want to thank the entire ARSET team. You might not have heard or seen us, but they've been working very hard in the background to make this training a success and possible. And that's Amita Mekta, Brittany Beaudry, Brock Blevins, Natasha Johnson-Griffin, Sarah Cutshaw, Selwyn Hudson-Odoi, Jonathan O'Brien, and Sue Monthie. So thank you to the entire ARSET team, and we look forward to seeing you all on Thursday for the final part of the webinar series. Thank you.